Welcome everybody. It's a great pleasure to have here Professor Edriss Titi. So he's a renowned expert in nonlinear systems and in particular models from fluid dynamics, having developed both analytical and computational tools. He has been undergraduate at Technion in Haifa and obtained his PhD in 1986 at the Indiana University Bloomington under the supervision of Cyprian Foyes. He has been then a Dickinson instructor at the University of Chicago and continued his career in California at the University of California, Irvine, where he became professor in 1987 until 2014. He has appointments at the Weizmann Institute for Science in Israel, Texas A&M University, where he is the distinguished professor, and since 2018, he's chair professor at the University of Cambridge. He's editor of many journals, such as Physica D, Journal of Mathematical Physics, Nonlinearity, just to mention some, and he has been member of several prize committees and advisory boards. He got, of course, several recognitions. Some of the most recent are the 2020 ICCM Best Paper Award, Fellowship of the John Simon Guggenheim Memorial Foundation, an Einstein Visiting Fellowship from the Freie University of Berlin, the Gaspard Monge Distinguished Visiting Professorship at École Polytechnique, a Senior Simons Professorship from the Polish Academy of Sciences, a Humboldt Research Award, and the Science Without Boundaries Scholarship from the Brazilian National Research Council. I chose this last one because he's really a person, I would say, without boundaries. He had, of course, broad knowledge and vision in mathematics, but also he collaborated with people from everywhere in the world and all backgrounds and cultures. So he kindly agreed also to give 2 more talks. So we're squeezing in like a lemon. So he will speak tomorrow at the Department of Mathematics at 3 p.m. And he will also kindly give the science class of science colloquium on Wednesday, still at 3 p.m., about mathematics of turbulent flows, $1 million problems. So don't miss that because there's money involved. So please.
First of all, I would like to thank you, Andrea, for the nice introduction. I would like to thank you for the invitation. It's very happy to see friends from the old times like Franco and Luigi, etc. And I asked Andrea how much time I have. He said, all the time that you want. So please lock the doors. No, don't worry. I tried to finish within 2 hours. Okay. So the title of my talk today is dispersion a stabilizing or destabilizing mechanism? And for those who basically are impatient to know the answer, if you'd like to leave early, then the answer is yes and no. So therefore, I'm going to show some examples when it's yes and some examples when it's no. And most importantly, it's not just to give examples, it's to understand the mechanism behind why things happen. So I try in some sense to connect the PDEs to a large extent with physics or with give some interpretation of the situation. So of course, I will start with the Navier-Stokes equations, u sub t minus u Laplacian of u plus u dot nabla u plus gradient of p equals to 0, and divergence of u equal to 0. And at the moment, I'm going to assume that I have periodic boundary condition. There are no boundary effects. And this is a problem in which we know from long time ago, from the 1930s, u of x0 is some given initial value. So from the 1930s, so Jean Leray, in the 1930s, he proved the following. If u0 is an L2 function in the domain, then for every t positive, there exists a weak solution. Exists a weak solution. And by weak solution means a solution which is continuous in time with values in L2, but with a weak topology. Intersection L2 in time with values in H1. Now, why this is important? Because I need to make sense of the initial value. So I need, in some sense, when t goes to 0, to recover the initial value. So, but we couldn't prove it like for a strong topology, but for the weak topology. So I can make sense of the initial value. And also that in the average, the H1 norm is under control because when I multiply by U and integrate by parts, I get the gradient of U square. And this is what's responsible for dissipating energy. Therefore, I need the solution to be here in order to make sense of dissipation of energy. Now, what he also proved that there exists a finite time T star positive depending on the initial data, for which you have a solution which is a strong solution. And by strong solution, we mean that the solution is continuous in time with values in H1, intersection with L2 in time with values of H2. So when I assume that the initial data here belonging to H1. So when you assume the initial data is smoother, then you get better regularity of the solutions. And this is basically the situation since 1930s for the Navier-Stokes equation. Now, if you go and look into the Euler equations, which is Navier-Stokes when the viscosity equals to 0, so U sub T plus U dot nabla U equals plus gradient of P equals 0, U diversion of U equal to 0. These are Euler equations. Now, the situation for Euler equation, in fact, has been shown before Leray. Leray is like 1930s, early 1930s, 32, 34. Now, the work about Euler equation has been done by Liechtenstein, 1925, before Leray, in which he proved the following result. If you zero the initial data belong to the space C1 alpha, namely one derivative is Hölder continuous, and alpha is positive, then there exists a short time T star positive depending on the initial data such that the solution is nice and belonging to the space C1 alpha. Now, you see he uses space C1 alpha, Hölder continuous, which are classical spaces, and therefore you expect that the guy used, in some sense, classical tools, okay, like potential theory and so on and so forth. Now, this is the situation for the Euler equation, but then it uses classical spaces. Now, what happens if you look at spaces like using more modern terminology, like Sobolev spaces? Of course, it's not modern anymore, but at that time, modern terminology. You don't want to look about classical spaces. Oh, so suppose the solution belongs to HS when S is bigger than 5 over 2. Okay, when S is bigger than 5 over 2, it has been the first work by Ebbin and Marsden, and then later by Kato and Fujita, and therefore they proved, again, short time existence and uniqueness of solutions in the space HS. Now, anybody who knows little bit of Sobolev embedding theorem knows that the space HS, when S is bigger than 5/2, is embedded in C1 alpha. So in some sense, this result did not tell us a new thing about the solution of Euler. It's just basically using modern tools of Hilbert spaces, if you want, or basically a terminology, which is modern terminology. I'm in Italy, so imagine that this result is written in Latin, and this is written in Italian. So it's basically classical versus more modern, okay? That's basically the idea. Very nice. And now, the question which was open for a long time, how about weak solutions? We know that you have weak solutions for the Navier-Stokes by Leray. Are there weak solutions for Euler equation? And this problem was open for a long, long time, until it has been settled maybe about 15 years ago only. And using the convex integration machinery, which was developed for the context of Euler equation by De Lillis and Sikahidi, and then for one can prove, in fact, there exist weak solutions for Euler equation. And in fact, the first result was they showed that the solutions are in L infinity in space and time. They are very weak solutions. In fact, their first result of the Lillis and Sikahidi showing that the solutions are in all space, are compactly supported in space and time, which means the solution are zero in now and in the past, and are zero in the future, and they are non-trivial in the middle. Okay, that's basically what we have shown. Of course, such solutions, at least the first attempt, it's not physical, because if there is no motion, there is no energy, how the fluid can start moving on its own? And therefore, nonetheless, they are mathematically okay. They satisfy the equation in a weak sense, so we cannot complain. Because when people wrote Euler equation, when I write Euler equation, I never mention anything about energy. It is a property of the solution if you know that there is a solution and it's classical, etc. So therefore, they proved there exists a weak solution. Now, for a long time, an open problem, and until now, are the Euler solutions which are satisfying energy inequality, are they unique or not? Are they weak solution? And it is really still an open question. We don't know if weak solutions of Euler, of Navier-Stokes, the weak solution, if they are unique or not. Well, we know that the strong solution, they are unique, okay? So this is still an open problem. And as said, until basically almost 15 years ago, 2010 or something like that, since the work of Liechtenstein, 1925, it has been an open question. What happens with Euler equation? Do we have weak solution or not? And many important people worked on that. And there was no answer to that question. But then we have weak solution. We don't have uniqueness. We didn't know about weak solution until about 15 years ago. And now, as I say in American English, when it rains, it pours. So basically, the methodology of proving existence of weak solution provided infinitely many, not only one. Oh, so do solutions of the Euler equation, weak solution, are they unique? There are infinitely many. Okay? So this is, in some sense, what's the situation with Euler. And this is not the topic of my lecture, but I have to put you in perspective to basically focus on the situation when I talk about classical solutions for Euler equation at the very beginning. Okay? So this is what we know about Navier-Stokes. That's what we see about Euler. Of course, there is some more progress about Euler equation and Navier-Stokes. This will be the topic of tomorrow's lecture. So this was a reclam, an advertisement for tomorrow's lecture. Okay? Now, we live on a rotating Earth. And because we live on a rotating Earth, then geophysicists think that rotation stratifies the fluid. And when you stratify the fluid looks like more or less like two-dimensional. Oh, it's interesting because the Navier-Stokes in 2D also proved global existence and uniqueness of both weak solutions as well as strong solutions in 2 dimensions. For Euler equation, one can show that classical solution exists and unique, and this was the result by Udovich, like if the vorticity is in L infinity, you have global existence. So in 2D, the theory is well understood. Why in 2D is well understood and 3D is not? Maybe I will talk about that tomorrow, but this is the situation. So now, because we live in a rotating Earth, and you look for the flow of the Euler equation, so therefore fast rotation stratifies the fluid and makes it look like two-dimensional. So maybe if I have large rotation, the equation, because it looks like two-dimensional when I have global existence, so maybe rotation allows me to show global existence. And indeed, this was the work of Babin Mahalov and Nikolayenko. In which they looked at Euler equation ut plus u dot nabla u plus the gradient of p plus omega e3. This is the vector direction times u equals to 0, divergence of u equal to 0, and omega is, say, a positive number, which is a rotation rate. So this is the Coriolis force, okay? So rotating. And what they proved the following result. If you give me initial data, u0, smooth enough, let's say it's in these spaces, I know we have short-time existence uniqueness. But now what they show there exists, so if you give me U0 and you give me a time you want, a time positive, there exists an omega 0 depending on time and U0 such that if omega is larger than omega 0, we have existence and uniqueness on the interval 0 capital T. It means you give me initial data. I know for short time I have existence and uniqueness. You want to prolong the life of span of the solution, you have to rotate the Earth faster. So this is exactly what this result tells you. In other words, if you would like to stabilize the climate, okay, you have to call for Superman so he can spin Earth very quickly in order to stabilize the climate. I think you saw all the Superman, the movie of Superman, when to prevent an event, he comes and rotates Earth backwards, okay, to stop the event and then come back. So this is basically the idea. If you rotate fast enough, you have existence of solutions for this equation. In other words, fast rotation is stabilizing the fluid. Now here is the question. Whether Euler equation has a singularity or not, we don't know yet. Of course, again, this is the topic of tomorrow. I will touch about some recent progress. But so I don't know if this rotation is indeed needed to stabilize the solution, or is it just basically a mathematical artifact just to make the proof working? So because I don't know if Euler blows up. So maybe if somebody tomorrow in some part in the world prove global existence of 3D Euler, I don't need the rotation. Okay? So then the question is, do I know some equation in which I know it has singularity, for which I can add rotation to it and show okay. Okay, so do I know of an equation which basically I know it has singularity in finite time, but if I add rotations to it, I get global existence, namely that rotation indeed stabilizing? Well, as you probably know, we don't have many equations in the world for which we know that you have short time, or basically you have a blow up in finite time. One of them is a nonlinear Schrödinger equation. The other one is more familiar, that we teach it for students depending on which university, sometimes undergraduate, but sometimes in the very first course in PDEs. And this is the equation of Burgers' equation. U sub t plus u sub x equals to 0. It develops a shock or singularity in finite time. Okay? And now if I give you the initial data, u of x at time 0 is phi of x, one can use the characteristic method and show that the solution u of xt is equals phi of x minus t of u of xt. So it is phi at this argument. And now, of course, one can use the implicit function theorem to show from this algebraic relationship that there exists a unique solution. If you would like to invert u as function of x and t, you can do that by using implicit function theorem and show short-time existence and uniqueness of solutions to the Burgers equation with a smooth initial data, namely phi is smooth, by implicit function theorem. However, if you look to ux, when I use the implicit differentiation, u sub x equals phi prime divided by 1 plus t phi prime, which means if phi prime is positive, the denominator is never negative, and they're never equal to 0, and therefore have global existence. So if phi prime is positive, namely, if the profile of the initial data is like monotonic, then there's no singularity for the solution. And in fact, this equation, one can think about it as a model for traffic flow. So basically, what means phi prime? Phi is the initial value of the velocity profile, and therefore phi prime is positive means this car is faster than one behind, and therefore they will never have a collision because you will never catch the one ahead of you. However, if phi prime is negative at some point, so if the profile is something like this, so there is a car that's basically slow. So if there is somebody here slowing down the back texting message, okay, checking the email while it's then basically you will have a collision. That's exactly what happens. So if phi prime is negative, then for indeed t plus phi prime, if t is equal to 0, this is 1, but for t large enough depending on phi prime, but at the point where it is negative, it develops a singularity in finite time. So this equation develops singularity in finite time. And now I would like to add rotation to this equation and to see that rotation is really stabilizing, namely preventing the shock from happening. But how could I add rotation for one-dimensional problem? How do I add rotation for one-dimensional problem? So you need to use imagination. That's what mathematics is all about. It's about imagination. Okay? So I need to introduce imaginary numbers. So therefore, let me look at the following complex Burgers equation. I replace x by z. I look for the solution ut plus u sub z equals to 0, u of z 0 equals some function phi of z, when I know that in some strip in the complex plane, phi is analytic. The initial data is analytic in some strip, and then I try to look for solutions of this equation. Of course, again, one can solve this equation and find that the solution satisfies property of this type. Therefore, you have short-time existence and uniqueness of analytic solution, because you should think about the derivative of u sub z is the derivative of regular or holomorphic function. It's a function of z as analytic function, because I'm assuming that phi is analytic. So I use the implicit function theorem here in the space of analytic function to show short-time existence and uniqueness. And now I would like to add rotation. So how do I add rotation? I add a plus I omega u. Omega is a real number, and I is an imaginary number. If I forget about that and I solve the ODE, u is e to the I omega t. E to the I omega, you add omega to the argument, and therefore omega times t, therefore it is like rotation. So this is a complex Ginzburg-Landau equation, and I would like to solve it. And then, to solve this equation, I use the characteristic method, and one can discover that the solution satisfies the equation u of x. So in order to do that, how do I solve this equation? Ladies and gentlemen, to solve that, I need to use the characteristic method. So I introduce the following variable, v of z and t equals e to the I omega t u, and therefore v sub t plus e to the minus I omega t v sub z equals to 0. This is exactly the same equation. And now I use the characteristic method and discover that v of z and t, notice that at t equal to 0, v and u are the same. And therefore the initial value, it is phi of z minus 1 minus e to the minus I omega t divided by I omega times v. This is the solution of this equation using the characteristic method. And again, this is the solution. So for short time, I have existence and uniqueness, and so everything is okay for this equation. With rotation, I have short time existence and uniqueness by the implicit function theorem. And now the question is, what could go wrong? The function could stop being differentiable. So let me compute v sub z, and therefore v sub z, if you do the differentiation, again, the implicit differentiation, it is divided 1 plus. So maybe I should really lower this. Oh, no, it doesn't work this way. Okay, I'm too short. Divided by 1 plus 1 minus e to the minus I omega t divided by I omega times phi prime. So the derivative of v is equal to this by the implicit differentiation. And now the problem was here that if phi prime positive, there is no singularity. But if phi prime is negative, there is singularity in finite time. Now phi here is a complex analytic. And because phi is complex analytic, suppose m is the supremum of phi prime of z when z is in the strip S. And now, if this quantity in absolute value is strictly less than 1, it could never be equal to -1, and therefore the denominator could never be 0. But this quantity is at most 2, the numerator, and the absolute value is omega. So, and this is like m. So if m times 2 divided by omega strictly less than 1, this is the upper bound on this quantity, then this quantity could never be equal to -1, and therefore I have no singularity, I have global existence. Let us read this. What this tells me, if the rotation fast enough, depending on the initial data, I have global existence. It's stabilizing. And this is indeed what happens in the result of Babin, Mahalov, and Nikolayenko, but you have to work very hard to understand what happens in Euler. You have to do some Diophantine equations, and so on and so forth. But this is a very simple example, tells you that there is a merit for that result and for Burgers' equation. Now, this is a beautiful mathematical proof, but I don't like. Why? I would like to explain it to a taxi driver, why rotation is stabilizing. Okay, of course, don't try to explain it to the taxi driver. They will know that you are crazy. Namely, you are a mathematician. Okay, so what's happening here? I gave you this relationship here. I gave you this proof, 2 basically lines, half a page proof for why rotation prevents singularity. But what's happening really? Other than this characteristic method and proof, what role does the rotation play? Okay, so let me look into here. And the best way to see it, I would like to see that V does not become singular. Therefore, if V does not become singular, then U does not become singular, because I multiply things by a factor which is different than 0. Now, if I look to this equation, and I look to its integral form, now integrated over the interval 0t, I get V of zt equals to the initial value, phi of z, minus integral from 0 to t, e to the minus I omega t, vv sub z, d, let's put it here, tau, d tau. That's what I have. And now, ladies and gentlemen, I have phi of z. So suppose phi of z is of order 100. And therefore, for short time, the solution V is like order 100. So this is 100, this is 100, 100, but 100 times 100 is 10,000. Is that correct? Okay? So it's 10 to the power 4, 10,000. But then, this is supposed to be 100. 100, 10,000, they cannot balance. I'm using now engineering proof, because I would like to tell you what really happens. Don't worry. This is like 10,000. By I integrate from 0 to t, I'll get like basically t times 10 to the power 4, 10 to the power 2, 10 to the power 2. If t is small enough, I can multiply by that and have a balance. That's why we can prove short time existence. This is engineering proof, huh? I balance stuff. But I showed global existence. Oh, this is remind me of 2 important people, okay, and their theorem, which is called the Riemann-Lebesgue theorem. What does Riemann-Lebesgue theorem? Riemann-Lebesgue theorem tells me that if you give me a periodic function, psi of x, okay, periodic function say in L2, then if I multiply it by sine kx dx, integral from 0 to 2 pi, then as k goes to infinity, this goes to 0. The same with cosine. In fact, how do you prove that? Because you can do the Fourier expansion, and by Parseval identity, the L2 norm of psi is the sum of the Fourier coefficient square, because the sum of the Fourier coefficient square is converging, therefore the series converging, the general term go to 0. This is it. This is the proof. So what this means if I integrate a function psi, which is L2 function, against something which is very oscillatory, it makes it very small. What is this? This is my very oscillatory. So yes, I have 10 to the power 4 against something very oscillatory. It makes it small, so I will have a balance for all time. That's why when omega large enough, like when k is large enough, you are okay. I rest my case. This is the engineering proof why the result is working. So oscillations is an averaging process over the nonlinearity, and therefore it is okay. So in other words, in Burgers' equation with rotation, which is I erased, the rotation, in some sense, averaging out the nonlinearity and make it milder. And that's why you have global existence. Now, notice that when I did the change of variables, I get very simple factor here. Namely, the terms, the nonlinearity v sub z and I omega v, these two terms, when I do the change of variable e to the power I omega blah, 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 this term, e to the I omega, pulls outside. Therefore, there is no resonance between the linear oscillation and the nonlinearity. And because there is no resonance, I do averaging, I see the effect of averaging. I get something nice. If there is resonance between the two, then I am in trouble, and therefore I cannot show that the nonlinear term becoming small. Now, why I'm mentioning that? Because Babin, Maholov, and Nikolayenko, to understand their result for the Euler equation, they have to work very hard, do Fourier expansion, and show that the resonance set is basically not there, and therefore they can really take advantage of that. That's why they have to solve an infinite system of the Fountain equations. These are the resonance set, and show that basically everything is fine. That's why their proof is very long and very complicated, but it is necessary because of the system. This is a trivial system. This is a toy model, and basically shows that if there is no resonance, everything is okay. Okay? So there is another result now. Of course, as I said, Euler equation, I don't know if it has global existence or not. Therefore, I don't know if the rotation needed for stabilizing. But for Burgers, I know it has a singularity in finite time. Therefore, rotation preventing singularity. I have another equation, which is I'm not going to talk about. And this is the primitive equation of oceanic and atmospheric dynamics. The primitive, and look for the inviscid primitive equation, or sometimes it's called the hydrostatic Euler. The hydrostatic Euler. And now we have shown, together with the Tsao, Slim, and Nakanishi, that the inviscid primitive equation develops singularity in finite time. Oh, so here's an equation which is inviscid, like Euler, but in the vertical direction I have the hydrostatic balance, which I know it has singularity. Okay? Which is the same like I have for Burgers. The question becoming, if I add rotation, can I show that the solution is prolonged? And the answer is yes. And this is a work of my former student, Chuan Lin, together with Slim Ibrahim. So indeed, for the primitive equation inviscid, I have singularity in finite time and rotation prolonging the solution. And exactly that we have the same result as Babin, Maholov, and Nikolayenko, but I don't know if Euler blowing up or not. I have another geophysical model, not only a toy model, namely the primitive equation of atmospheric and oceanic dynamics, where I have basically again that rotation is regularizing, namely stabilizing the solution. Okay? So far. Okay, now that I have mentioned all these nice stuff, let me move on and talk about another equation in which the situation is not as trivial as I would like it to be. And this equation is again Burgers' equation. Ut plus ux. I know this has a singularity in finite time. Now, if I put at viscosity, one can show that the viscosity is smoothing the solution by basically acting on the small scales. Because what is the shock? The shock is basically your support. Shock is very fast. The gradient is very large. It means there is a phenomena that takes place at a very, very small length scale. Viscosity smooth it out, and therefore you have a global existence by adding viscosity. This is one mechanism to show regularization effect. You can add minus in u, uxx equal to 0, and this is regularizing, but through viscosity, namely through basically dissipation of energy because of this term. But this is not the only mechanism that you regularize Burgers equation. There is another equation which is regular, ux, but then I have uxxx equal to 0. And this equation is called the KdV equation of waterways, okay? Now this equation has a global existence and uniqueness. And now suppose I'm looking for a case of periodic boundary condition. You can see that this is 1/2 u square x. This term is called the dispersion term. Okay, this is the dispersion term. And now, if I look to this equation and try to understand what's happening with this equation, okay, I assume that the initial value has averaged from 0 to 2 pi u0 of x dx equal to 0. I'm looking for periodic boundary condition 0 to 2 pi, and the initial value equal to 0. If you integrate this equation, because it's periodic, this disappears. Because it's periodic, this disappears. And therefore, the average of the time derivatives, the time derivative of the average is constant, 0. And therefore, this is remains 0. And this is, as a result, implies that the average of u of xt dx from 0 to 2 pi equals to 0 all the time. So I'm assuming that the average is 0 for the initial data, therefore it's average for all the solution. In other words, if I do Fourier expansion, when I do the Fourier expansion, therefore the 0 mode, or the 0 is 0, it's not there. I have all the modes except 0. And now I would like to solve this equation, so bear with me. I'd like to solve this equation. Again, nothing in this lecture is very technical or very, but I'm just basically trying to shed ideas or shed light on problems. And now, suppose I take the Fourier transport or Fourier transform of this equation. I do Fourier expansion in Fourier series because I'm periodic boundary condition. And therefore, I will have u hat k with respect to t plus, this is a derivative, it is ik over 2 summation. It becomes the Fourier transform of a product of u square, which is a convolution. So it's summation of u hat of k1 times u hat of k2, k1 plus k2 equals to k plus I k cube u hat of, with minus sign, okay, uk equals to 0. Very simple. Now, ladies and gentlemen, if I take my Fourier equation, my Burgers equation, if you remember, my Burgers equation, if you remember, I have like so I have ut plus u sub x plus I omega u equals to 0. Allow me, I just call it x now for a second. Do you see if I take Fourier transform, Fourier transform, Fourier transform, this is the same like this. This is the same like this. And now I have I omega u transform. I have here ik cube. So the ik cube here, it is like playing the role of omega. But now it is wave number dependent. And I needed omega to be very large. Hey, if k is very, very large, omega is very large. Now we know that this equation, the L2 norm of the solution is constant, is conserved. Therefore, if something goes wrong with this equation, is not the L2 norm, namely not the low modes, because all the low modes are bounded in L2, therefore they don't go to infinity in finite time. It's not possible. So what goes wrong is the high modes. So what I need to control is the high k wave numbers. And that's why I'm going to capitalize on this ik cube and use it to show why I am basically under the right conditions for controlling everything. So what do I do now? Don't think much. Repeat what you did for Burgers. So the exchange of variables, and now I define vk hat to be e to the minus ik cube t uk hat. I did e to the minus I omega. I do the same. And now, what happens here, you discover that V hat K sub T from this plus IK over 2 summation. I have here e to the IK1 cube plus K2 cube times e to the minus IK cube. Everything multiplied by T. This is coming from this change of variables equals to 0. Oh, I say the coefficients. I have VK1, VK2 hat equals to 0. And this is K1 plus K2 equals K. So you can see that I have this term here, e to the power I pull the I outside, and I have here an I. I have an I here. You see, this is now playing the role of omega, which depending on K1 and K2. And now, if I do average, I have to basically average in time. I need this quantity to be not 0 because I wanted e to the I omega t. So I need somehow to have exponent. Otherwise, I'm not integrating against oscillatory power. And now the question, is omega equal to 0? If it's equal to 0, then I'm in trouble. I cannot continue for some wave numbers. Now, what happens for omega k? Omega k is exactly like this. It is basically k1 plus k2 cube. This is this term because k is equal k1 plus k2 minus k1 cube minus k2 cube, which is, if you open the arithmetics algebra, it is a 3 times k1 times k2 times k1 plus k2, which is k if you want, huh? This is k. And now the moment of truth. I told you that the average is 0, so the wave number can never be 0. So K1 cannot be 0. K2 cannot be 0. K1 plus K2, which is my K, cannot be 0. So this term is never equal to 0. So I see oscillations. There is a hope. And now, let me tell you something. If I integrate this equation, because I like the integrated version of Burgers' equation to show you the averaging, and now I have the integral of this quantity, e to the omega. Here it is. I have the integral of e to the I omega times this. I integrate by parts, but in time. I will integrate by parts in time. I will have here 1 over omega. 1 over omega means I divide by 3k1, k2, k. When you divide by k, you regularize in space. Oh, so the averaging leading to regularization in space. And this derivative here, k, and this k cancel. I don't see anymore the derivative in the nonlinearity in Burgers, which forming the shock through the averaging process. And even more than that, I divide by K1 and K2. This means I have one spatial regularization on the first V1 and another spatial regularization V2. Wow, this means this process, if it works, then everything is fine. Except when you integrate by parts in time, what I'm going to have, I'm going to take the derivative of this with respect to time times this. When I differentiate this with respect to time, I have V of K1 in time. But then when I do that, I will have here K1 times quadratic. So therefore, the K1 and the K1 cancel. And then I have only, I will have here like a order. Here is quadratic. But when I do that, I will be getting like polynomial cubic kind of like term. So on the expense of basically getting nicer regularity in space, the inequality, sorry, the nonlinearity become higher order algebraically, not derivatives. We are doing PDEs, not ODEs. In ODEs, when you increase the power of the nonlinearity, maybe there is singularity unless it is the right sign. But in PDEs, more derivatives in nonlinearity is more trouble. Here I gain regularity in space, but then at the expense of having basically now polynomial nonlinearity. And this is basically, in some sense, the upshot of why we can show global existence for this. And this is a joint work with Babin, Elian, and myself. Okay? However, some of these ideas has been introduced for the KDV by Bourgain to understand why you have regularity for the Burgers equation in the periodic boundary condition for very weak solutions, and so on and so forth. But then they use, Bourgain using some kind of like a harmonic analysis. They look for something about other invariant quantities. And this is really straightforward. I mean, in this paper, you can really read and see basically straightforward the calculations that any student can really follow, any freshman graduate student can follow to see the proof in this, for this equation. So, this means this term, UXXXX, which is the dispersion, which is basically, it is like e to the ik cube, is in some sense stabilizing. And what does it do? Actually, because you do averaging on the nonlinearity, it makes the nonlinearity milder. Because there is no resonance. What does it mean there is no resonance? Because the ik cube, this term, and the ik1 square, q1 cube, and k1 to q, when you took to the difference, it is not zero. It means there is no resonance between this term and the nonlinearity. Because there is no resonance, everything is okay. Lucky again. We are lucky again. So dispersion is stabilizing. And what does dispersion do? Because there is no resonance, through averaging mechanism, it makes the nonlinearity weaker or milder. So here's another example in which basically we show that the dispersion is doing the right job. For Euler, it's rotation like dispersion. Averaging is okay. So I would like to call it more averaging rather than dispersion, because I'm doing periodic boundary condition. If it was on the whole line, it is dispersion. But now I'm doing periodic boundary condition, so it is a form of averaging. Okay? Okay. I didn't say if you have resonance, it does not work. I'm showing that if there is no resonance, it works. If there is resonance, guess what? You have to sweat a little bit more. You have to deal with the resonance set. The non-resonance set goes by this method, and then you have to focus on the resonance set, and hopefully, maybe you can show that the resonance set is maybe a system of ODEs that you can control, and everything is fine. Because it is a discrete set. There is a certain, I have K1, K2, and K, therefore I need to see when some quantity equal to 0. So it's not for all the Ks, because I have K1, K2 in the whole plane. Now it's going to be like maybe on a line. And the question, and that's what happens sometimes when you try to do this theory on the whole, like using Fourier transform instead of Fourier series, then the resonance set will be in the plane, is a line or a curve, which has measure 0, and therefore, now you have to sing and dance to show that everything is working. Okay? Very good. So now, after I have shown this situation, so far I have been lucky, and have been showing to you dispersion is doing a good job. Now it's time to show that dispersion is destabilizing. So I need to give you another model in which show you that the dispersion is destabilizing. So now I'm going to take another equation. So UT plus UUX. Oh my God, I keep starting with burgers. I don't know anything other than burgers. Okay, burgers is a very good equation, which gives me all what I need to know. And now I add the following term, UXXXX, for derivative. oh, this is a very strong regularization mechanism. It is double the Laplacian. So therefore, it kills the high frequency very, very quickly. So this equation is super nice. With viscosity, I'm nice. With super viscosity, hyperviscosity, I'm even better. But now, I'm going to have this term plus u xx equal to 0. Somebody might scream. He says, did you mean a wrong sign here? You put plus. Shouldn't it be minus? No. I wanted it to be plus. I want basically to be backward heat equation. But now, ladies and gentlemen, there is fight between this guy, which is stabilizing, and this guy, which is destabilizing. And the question, who's stronger than who? This equation called the Kuramoto-Sivashinsky equation. And I'm looking to it periodic with period L. Periodic boundary condition with period L. Again, this is a complete derivative. I'm assuming that the initial data has average 0. And therefore, one can show that the average remains 0. This is first thing. But I'm going to do something more. I'm going to look for the invariant subspace of periodic functions which are odd functions. Oh, so is this space invariant? Yes. Because if you take odd function, you take 2 derivatives, it remains odd. 4 derivatives remains odd. 1 derivative, oops, becoming even. Times u, which is odd, the product is odd, and the time derivative is odd. So therefore, the odd space is invariant. Therefore, if I do the Fourier expansion, it will be only Fourier series with respect to sine kx. Now, instead of looking at this equation, let me look at the linear part of this equation. I call it Wt plus Wxxx x plus Wxx equals to 0. And again, I do periodic boundary condition, and I take initial data, sine kx, and I look for a solution ak of t times this. And I plug it into the equation, and therefore I get from here that ak dot plus ak multiplied by 2 pi k divided by L to the power 4 minus 2 pi k over L square equals to 0. So the solution with this of this type would satisfy this relationship. And now the question is, what's the sign of this quantity? If the sign of this quantity is positive, then I have, when I bring this a negative, ak is going to 0. This means the solution is going to 0, so it's stable. And if the sign of this is a negative, I bring it to the other side, become positive, and ak is growing exponentially. And indeed, there is a particular wave number, k star, which is 2 pi over L. Okay? Here is basically wave number 1, etc. Up to here, okay, this is stronger than this. And as a result, all these Fourier modes here are unstable, and therefore, I increase the solution exponentially fast. And what if I am here to the right? This is stronger than this negative, and therefore, I exponentially decay, and everything is going to 0. So the linear equation is unstable. Why? The low modes are going to infinity, and the high modes are going to 0. So it's a fight between these two guys, destabilizing and destabilizing. Okay? But this is only the linear scenario. What about if I add the nonlinearity? What does the nonlinearity try to form? Forget about these two. Burgers. Burgers trying to form a shock. The L2 norm before the shock is conserved. So all the modes have the same energy. But then there is a singularity, namely the gradient becomes infinite because I have infinite, the solution becomes discontinuous. It means that I am transferring energy from low frequency to high frequency. I'm cascading energy. The nonlinearity, through the process of trying to form shock, takes energy from the low modes to the high modes. Oh, thank you very much, nonlinearity. It takes energy from here to here. In other words, you produce energy at the low frequency, Nonlinearity is a highway that takes the production of energy from the low frequency to the high frequency, and the hyperviscosity, strong enough, consumes it very fast, and we finish. So you produce some corpse in the field, you have lorries, which is nonlinearity, take it to the city, and the city, always hungry, they can consume all the vegetable you produce. And now the whole orchestra working beautifully to show that this equation is stable. So, by the way, a remark here for the young. Don't you see the linear equation unstable and the nonlinearity stabilizing? Oh, the nonlinearity is not always a bad guy. Nonlinearity is not always the bad guy. We always try to fight against the nonlinearity. Here, the nonlinearity is helping me. Without the nonlinearity, I cannot prove it. Of course, this is an engineering proof again, but there is a rigorous proof. So the nonlinearity is stabilizing. So nonlinearity is the highway. So because it's a highway, with your permission, I'm going to basically put many lanes here, coming from here to here. Okay? So this is equation which is stable, and everything is nice. However, suppose I would like to add here plus alpha 3 derivatives. This is like KdV, but Kuramoto-Sivashinsky. And alpha is large. What happens now? What does this guy try to do? If I forget about these two, alpha 3 derivatives, the dispersion term, it makes the nonlinearity weaker. That's what I have been showing you about KdV. It means that basically make this highway narrow, and more narrow, and more narrow. So therefore, yes, you produce energy here, but the vehicles to transport the energy becoming weaker and weaker and weaker. And therefore, at the end, you are in trouble somehow. In other words, the dispersion now, because it makes the nonlinearity, which is the stabilizing mechanism, weakened, therefore the dispersion now is destabilizing. And now, to show this result, this is a result with Kostienko and Zilic. Self. We prove the following, that if you give me, this is the space L2, and you give me a ball of radius r, no matter how large is r, let's take r very, very large, but fixed. You take ball of very, very, very large. And now, there exists an alpha, 0 depending on r. And suppose I take alpha to be larger than this alpha 0. Okay? This means I take the dispersion coefficient large enough depending on this r. Now, let us look into the solutions of this equation. Do you agree that 0 is a solution? Yes, it's a steady state. Now, if I take any initial condition in this ball, no matter what, the trajectory cannot be confined in the ball. It has to go outside. Maybe it comes back, but it has to go out again. It could never be confined inside the ball. This means the solutions have big excursions, becoming unstable, becoming large amplitude. And this is because of the dispersion. I take a larger ball, I take a larger dispersion, and therefore I could never stay all the time bounded by R. I remain bounded, but not by R. And this is really manifestation of destabilizing. So everything is unstable except 0. I start with the steady state. Yes? Well, of course, I mean, the length, of course. Everything is depending on the length. Yes, of course. Yeah. Thank you very much. Very good remark. Yes. L is fixed, but I'm trying to basically now take a large ball. Okay. Okay. So far, we are okay. Can you take one more thing? So I'm still on page 1. So no, I'm fine. Okay, so now I'm going to talk about, somehow, if possible, I would like to talk a little bit about Landau-damping. Okay. Again, as you can see, my lecture is not very technical. I'm not talking about like the most technical part and stuff like that. I'm oversimplifying things. It's maybe unfair. It's unjust, some sense, because people sweat and work very hard to prove a theorem, which basically big papers and then take forever to write and then being up. But then you just basically give like a small lecture to basically show why it works or why it does not work. So now I'm going to talk about Landau-damping. Okay, I'm going to first motivate what I'm going to talk about. And one of the very first rigorous results one of the very first results in this direction is due to Colloquio and for the Vlasov-Poisson equation. So the Vlasov-Poisson is dt of f plus v dx of f plus e dv of f equal to 0. dx of e equals rho minus some rho 0. And rho is the integral of f of x, v and t dv. Okay? So the idea, if you look for homogeneous solution, if you look for a solution f is h of b, look for solution, and the electrical is 0, then one can show that this, and therefore the integral of h of v dv equal to rho 0, then if f becomes non-homogeneous in x, the idea is to show that f of x, v and t is like some function f star of x minus vt v. So the idea is to show that the solution of my equation is like a function of two variables, only x and t, but the dependence on v through the translation. And I'm looking for this system periodic on the circle on S1. I want it to be periodic with respect to x, because everything is function of one variable. And now the result here basically shows the following. The result, what they show, is basically that there exists such a function f star, such that f of x, v, and t minus f star of x minus vt, v in L infinity in space, and v is going to 0, okay, as t goes to infinity. In other words, the profile of the general solution is captured by some kind of like uniform profile. And in fact, one can show that the limit as t goes to infinity of f star of x minus vt, comma t is equal to h of v, and this limit in the sense of weak limit. Okay, that's what would happen. And h of v is basically the integral of f star of xv dx 1 over 2 pi. This means the function h, where you converge to it, is in some sense is the average with respect to x. Okay, so do you see now everything will maybe connect together with what I said all the day? I have a function which is the periodic in x, and now I have x minus vt. X minus vt. V is anything. Therefore, when t is very, very large, x minus vt, I'm going around x very quickly. When t is very large. And therefore, I'm averaging with respect to x. because f is periodic function of x. And therefore, you average, so this limit, h star, is the average with respect to the x variable. Okay? This is the result of Colloquio and Moffett for this Vlasov-Poisson equation, showing Landau-damping, which means, roughly speaking, that you need to find that if you give me a solution of this equation, it is behaving like a profile f star of function of two variables, but then this is x minus, therefore you have to look for a different frame of reference. You have to go with a frame of reference minus vt, and therefore you show that this is equal to this limit, and this h is exactly this average. This is the result. Now, I'm going to pick up only one thing. I would like to basically pick up this part. Namely, I'm not going to prove this result. I'm going to give you an analog of the Landau-damping for the 3D Navier-Stokes equation. Okay? Of course, the best result in this spirit, but in the context of Euler equation, is to Bedrosian and Masmoudi, in which they looked for the solutions of Euler equation, and they look for the solution of the Euler equation in a strip. This is x, this is 0 to pi, and this is the y, is infinite dimensional, y. And they look for a background flow, which is in the y direction, which is a shear flow. And then they look for solutions around this shear flow. And now, because you are periodic in x, and if you take a point here, it goes around very, very, very fast and averages. Again, my goal is not to talk about their result, which is very nice, very beautiful, but it is really more involved. But I would like to give the idea. And the idea, what they do here, is inspired somehow by looking or guessing a profile, which is you need to look for x minus vt. You need to take some kind of like a moving frame of reference. And then when you go to a moving frame of reference, in fact, you get a very good approximation for f if you can guess f star correctly. And in fact, one can show that f minus f star is going to 0 in this norm, and that the weak limit of f star is h of v, which is a non-homogeneous solution. Okay? It is basically like steady state. Okay. Now, what is the problem I'm going to talk about? And by this I quit. I know it is like basically becoming the time. What's the result I want to talk about? I'm going to talk about the Navier-Stokes in 3D. And this is a joint work with Mucha, Dr. Mucha, plus co-workers. Okay? So it's a joint work with Mucha and some other people. And the idea is to look at the 3D Navier-Stokes equation. I look at 3D Navier-Stokes equation. Again, I start with Navier-Stokes, I end with Navier-Stokes. So the Navier-Stokes equation is d dt minus nu Laplacian u dot nabla u. Now I put a forcing f, which is time independent. Force of x, divergence of u equals to 0. And f is a force which is time independent. And I'm in 3 dimensions, so I'm doing periodic boundary condition. So I'm like in a torus in 3 dimensions, okay? Now, one can show easily that assuming that the average of f dx is 0, assume, and that the average of the initial value dx is 0, it implies that the average of u dx on the torus is also equal to 0. Therefore, the average is invariant. Okay? This is what happens. Now, I know that this equation has a weak solution, a Euler, a global weak solution, but I don't know if it's unique. And if I take f very, very large, and I'm going to take f very, very large, namely I shake the fluid very vigorously, and take viscosity very small, this means I hardly dissipate the energy, therefore I will get turbulent solution. And now, assume that the initial value, u0 of x, I don't want it to be 0. I want it to be some number, omega E1. Namely, it is in the x direction, a flow in the x direction, not 0. This means the initial value is given not to be 0, the average of it. And I'm assuming that omega is very large, and we will see what happens. I would like to take omega very large. And F is very large. And in U, very small. Means I'm very turbulent. And even I'm initializing the flow with large velocity. Okay? Now, what do people do to solve this equation? I do change of variables. V of xt is U of x plus omega E1t and t. And then I have to add here plus omega t E1, or minus actually. This is the Galilean transformation. I move with a constant velocity with the frame, and I have to case with this. And we know that Navier-Stokes is Galilean invariant. And therefore, E, the V equation, satisfying this relationship, ddt of V minus nu Laplacian V plus V dot nabla V plus gradient of P. Did I put here gradient of P? No, I forgot the gradient of P. Plus gradient of P. So maybe different P here because I changed variables. Q is 1 f of x minus omega E1 of t. Divergence of V equal to 0. Now, all what I want is that the 0 mode of f in the x1 direction, I would like to understand f of x dx1 over the circle equals to 0. Namely, I don't have 0 mode in the x1 direction. So k1, k2, k3, k1, when k1 equal to 0, the Fourier is 0. And now what happens here, ladies and gentlemen, you can see when omega is very, very, very large, because I'm going in the x1 direction, and the 0 modes of the x1 direction is 0, so this is going very fast. It making f very, very small. When f is very, very small, I know from the Ray result, if the forcing is very, very small, 0, then the solution eventually becoming nice. So what's the result that we prove? We prove that there exists a unique V periodic solution of x and t when omega large enough such that any solution of this equation, V minus V periodic, is going to 0 as t goes to infinity. And in fact, this periodic solution, we can show that it is small, smaller than some number delta. You give me delta, as small as you want. I choose omega large enough such that there is a unique periodic solution of my Navier-Stokes, which is very, very small. And the general solution is converging to it. This is the result of these people, Galeotti, etc., etc. So in some sense, it is when I go to this. Remember this transformation plus VT, what they said? I do, but in my case, it is not an ad hoc. It is the natural Galilean transformation. In their case, they have to basically be smart enough to choose V, xt, etc. In the case of Bodrosian and Masmoudi, it's even more complicated. They cannot do. They have to take a nonlinear function, not omega, like phi of x and t. You have to adjust in order to show that the profile f star is attracting. Here is really trivial. I solve this equation, and I show that this equation has a time periodic solution, and this time periodic solution is small and attracting. All right, I start with f very, very large, viscosity very small, omega very, very large, very strong turbulence. But then if I wait, going everything to converge to a time periodic solution and very small. Goodbye to turbulence. This means this omega basically stabilizing. And all because of averaging process, because I am periodic in the x1 direction, and the 0 Fourier mode in x1 is 0. Therefore, When omega is very, very large, I'm averaging, and therefore F in the average becoming small, and as a result, I'm fine. So this is a version of Landau-damping, if you like to call it, for 3D Navier-Stokes. So therefore, omega very large suppresses turbulence. Now people says, yes, this is good mathematics. What's happening? Why when omega large, you suppress turbulence? Because I'm periodic boundary condition. So I have turbulent flow. I have small eddies here and small eddies there and going all over. But now omega is a background flow, which is very fast going whoosh around. And while it's doing is basically take all the eddies and basically take them around and around and around very quickly, such that it homogenizes them and averaging them to basically end up like having time periodic solution that you converge to. That's the simple engineering explanation for this result. But mathematics is basically you need to do the transformation. Thank you very much for your patience. I appreciate it. And thanks again for the invitation. Thank you very much.
Edriss, for the great talk. Is there any question?
So is this result also valid for nu zero, or is the mechanism?
No. You need viscosity.
Okay.
You need viscosity.
So nu is very small, but you need it.
Yes.
So there is no Landau-damping for Euler.
Yes, there is one for Euler, damped Euler.
Okay, damped.
No viscosity. I don't need really viscosity in the sense of smoothing, but then I need damped Euler. But I don't know if damped Euler has a global weak solution in this sense, etc. So I need some damping mechanism, whatever here. So it is different than basically the 2D Euler. The 2D Euler, they linearize around a particular flow, which is in some sense mixing, because the larger Y, the faster the particles are moving. And therefore you have strong shear, which is mixes, and everything is fine.
Perhaps a naive question, since you mentioned periodic homogenization, is there something with stochastic homogenization, so some effect with the randomness?
I cannot speak in front of the person here, so I don't know. I mean, I'm not really. We had all this afternoon fight about. He tried to teach me stochastic, and I'm basically has a closed mind. I couldn't understand, so I don't know much about stochastic. But maybe it is. Maybe it is. Maybe it is. Maybe one has to really look to the mechanism of why basically averaging stochasticity leading to kind of homogenization somehow, or basically reducing the turbulence effect. As I told you here, omega very large make the forcing small. Forcing small is basically Navier-Stokes with almost no forcing. Then we know everything go to zero. But now I don't go all the way to zero. I have some forcing a little bit, which is basically to sustain, because omega is not equal to infinity. Omega is very large. And therefore, I will have like basically, it is small in some sense, but then it's periodic in time. Therefore, I converge not to zero, I converge to time periodic solution. So I don't know what will be the analog in stochastic. It'll be nice. I mean, as I said, this is very simple Reader's Digest version of what's basically happening in the field. Okay, as I said, this is my, and I didn't do anything technical. Of course, there are some proofs behind every statement, but. And again, for me, this was all inspired by the work about Euler-Poisson when you take x minus vt, in my opinion. And I said basically x minus omega t. That's all what I did here. But this is Galilean transformation. There it is not really, because v is not constant. V is part of the solution.
It's not a question, it's a remark on what you said. If you rotate in both directions, of course, it becomes more and more turbulent. So stochasticity in the sense of very fast bidirectional rotation is not the same physical mechanism. However, the possibility is that a strong turbulence regularizes.
Yeah, it's suppressed.
Suppressed. So maybe the strong turbulence.
And as I said, the explanation I gave to you is basically I have one direction, and then I have a background flow, like storm going around very quickly. And therefore, it takes all debris and all the junk around with it. And then it takes it with it. And then when you look after a while, it looks like something going around periodically. You forget about the details. The details are averaged out somehow. That's what's happening in this case. In one direction, it's easy. So, for example, this is a good point. Suppose I take something periodic in two directions. So omega is going in two directions. But now, if the two directions may be irrational or rational, I need to go some ergodicity. Well, I don't know what's happening there. So this could be a nice question to see. Like you don't go in one direction, but you go in two directions, and are they dependent on each other or not? So if they are really not rationally dependent in two directions, what happens? Therefore, if I go rational, but then I cannot guarantee that F is periodic. So unless I take maybe two periods, L1 and L2, whatever, then I don't know. But this is a good question.
That question, but just to be sure. So you're saying that this, in your Reader Digest, the explanation, it was really important that the omega E1 hat was in parallel to one of the periods.
Yes, I took it here because it's easy for me to explain it to you.
Yes, but one would expect that.
But you can go in the other direction as well.
No,
but notice that's the condition. I need this condition, that the average with respect to x1 is 0.
Yes.
So if you have the 0 Fourier mode, all of them are 0. K1, K2, K0, all of them 0. But then there's nothing. You see what I'm saying? I need 0 mode to be 0, so I can have average in the x1 direction.
So it's not clear what would be the analog if you have like an irrationally, not rationally commensurate.
Well, one has to check into that, yeah. One has to see. But you need to make sure that F will be periodic. Yeah. So if they are rationally dependent, yes, they are periodic, but then you come back into the same story.
Yes.
Okay? Because then you rotate because the equation is, you see, the equation is Galilean invariant under translation, but also under rotation. So I can rotate the coordinates and then becoming like in one direction, and then I do the same thing. So instead of taking x minus plus omega t, I do rotation on x minus that. And therefore I go basically now periodic, but then the torus will be now a different torus, rotated torus. It could be. This is just basically my most naive ideas about how to address such a question.
Thank you.
Sorry, I have a naive question about the Euler equation. So there are these solutions that start from 0 and then disappear. Yeah. So I was wondering whether maybe there should be some other notion of solution, and whether, I don't know, for example, can you select them by monotonicity of the energy, or?
If I tell you the answer now, I will not see you in my lecture tomorrow. No, actually, we propose some selection mechanism. But again, the verdict is still out there. I mean, the suggestion, for example, Bardosa and myself, is the following. Any solution of Euler, any solution, weak solution of Euler, which is not a limit of Leray-Hopf weak solutions of Navier-Stokes, should be ruled out on physical ground. And we give enough evidence why this should be the criteria. It's not a proof, it's not a theorem. On the other hand, recently in the thesis of one of my PhD students, basically we show that not for Euler, but for the kind of like a passive scalar, or basically the transport equation, the viscosity limit mechanism is not a good mechanism for selection of physical solutions. I will talk about that.
You said not a good selection?
Not. Okay. But that's for passive scalar. Okay, so now what happens if you have active scalar like Navier-Stokes? Think about Navier-Stokes 2D, like vorticity is an active depending on you. What happens there, I don't know. But that's why it is a suggestion. And I have some evidence of why this is at least rules out trivial solution like the one you mentioned, namely, do not become 0. Look, their solution is you start 0, then you become non-trivial, and then you become 0. Now we know that the physical solution, if you start 0, you should remain 0. Now what we can prove is the following, that if you take Navier-Stokes, Leray-Hopf solutions with initial data 0, the only solution, because it is a strong, and you know we have uniqueness, weak, strong uniqueness of Leray-Hopf solutions. This is Seren result. Therefore, the only solution for Navier-Stokes, Leray-Hopf is 0. And now when I let viscosity go to 0, the only thing I get is 0. Therefore, any solutions of Euler starting from 0, which is not 0 all the time, by this criteria should be ruled out. because cannot be achieved as a limit of Le-Hopf weak solutions. Now, Le-Hopf, they are not unique by themselves, but then I need subsequences of viscosity to converge, so maybe I capture something. This is the suggestion. I will give some more examples to give an evidence of why could be a good or legitimate criteria, but we don't know.
Okay, thanks. All right, so if there are no further questions, we can thank Edriss again.
Thank you very much again.